Hello, I'm Hugh Manfield and welcome to my science channel. Now today I'm going to be talking about Hermann Minkowski and Minkowski space. Now, Hermann Minkowski was not just a dapper fellow with an excellent mustache. He was much more than that. He was a gifted mathematician and a physicist. And by that I mean he could picture and visualize how to apply the abstract mathematics to the physical world. Minkowski was born in 1864 and tragically died in 1909 from an appendicitis. Now, I've had an appendicitis and it's not something I would wish on anybody. However, I was able to survive due to the modern medicine, and I'm here now able to talk to you about Hermann Minkowski. Now, the information I'm going to provide today comes from this book, Minkowski Spacetime, from the Minkowski Institute. And in this book, it is explained how Minkowski arrived independently at a version of special relativity concurrent with Albert Einstein. However, Albert Einstein published first, and Minkowski was generous not to challenge that and to work with Einstein, developing Minkowski spacetime. If we look at the timeline, Minkowski was born about 14 years before Albert Einstein, and between 1910 and 1905, Minkowski was actually a professor at the same institute where Einstein was doing his graduate studies. Einstein did a lot of his graduate work kind of by correspondence while he was working at the patent office. So it's not exactly certain how much time Minkowski spent face-to-face with Albert Einstein. Now, Einstein had a very different philosophical approach from Hermann Minkowski. And if you read Einstein's books, and these quotes come from his book on the special and general theories of relativity. Einstein's approach was what I classify as a space denial approach, and it stemmed from the ancient Greeks, and I'll go into that philosophy and why he believed it a little bit later. But basically, Einstein would say, in the first place, we must entirely shun the vague word space, of which we must honestly acknowledge we cannot form the slightest conception. Well, I disagree with that, and I think Minkowski would disagree with that. However, we'll continue on. And we must replace it by motion relative to a practically rigid body of reference. Now, this you can see in Einstein's writings over and over, where he always speaks of we must focus only on objects, material bodies, and not on space. So he carried the space denial philosophy through most of his work, even to the point where he had to declare electric and magnetic fields as physical bodies, so that when they were applied to a Lorentz transformation, it was applied to a body and not to the space. However, how you can length contract and time dilate an electromagnetic field without doing that to the space it occupies is a little beyond me. Einstein's space denial philosophy dates all the way back to the ancient Greeks and the theory of the atom. If we look back at our timeline, we'll see that when Einstein developed special relativity, it was still 6 or 7 years before Rutherford would be doing his scattering experiments and working with Niels Bohr to develop the Bohr atom. So in 1905, when Einstein was working on special relativity, the thought of the day was the matter existed as atoms, which were small individual pieces of something, some kind of substance, and they could have been spherical or possibly have geometric shapes similar to maybe the Platonic solids, which are shown here. The philosophy was that there was substance and there was void. Void was void and substance was substance. There wasn't an intermixing of these two things. And when Rutherford set out to do his scattering experiments, he was figuring that if you have a sheet of aluminum or gold, I think maybe what he used, some sort of metal. It would be made up of these atoms packed tightly together, possibly as spheres or maybe as cubes stacked in like bricks. And anyway, when you projected a particle against this foil, it would rebound. And from the rebound angles, you could figure out what the shapes were. If it was spherical, you would get a spherical rebound distribution or a circular rebound distribution. And if the atoms were maybe rectangular, you would get the rebounds bouncing off at a predictable angle, all concentrated at the same direction. Or maybe if it were dodecahedrons, all packed in the same orientation, you might get three different rebound directions where everything would, on average, rebound in those directions or pass through the material in the gaps between the atoms. And this was the state of thinking in 1905. And when Rutherford actually ran his scattering experiments, he was surprised to find that all of the alpha particles, which he was using, passed through, or almost all of them. Hardly any of them were reflected. And the number that were reflected indicated that the atoms, the solid part that would bounce alpha particles off, were actually very, very small, highly dense concentrations at the very center. And this was a total surprise. Now, Minkowski had a different view, and it came from his background in mathematics. And in the book, one of the quotes that stuck out to me was when Minkowski said in one of his lectures, talking about four-dimensional space-time, hereafter we would then have in the world no more the space, but an infinite number of spaces, analogous as there are an infinite number of planes in three-dimensional space. So Minkowski had a spatial approach, a geometric approach, which didn't deny the existence of space, but accepted the properties and the different possible levels of space-time there could be. Now, to understand this better, we can look into the space-time diagram. And Minkowski was key in developing space-time diagrams, and he used them extensively in his lectures. Now, space-time diagram, basically you have space along the horizontal axis, and I'll call it the x direction, and you have time going forward on the vertical axis. And you locate a arbitrary 0 point for the origin. Well, this is the basic space-time diagram. Now, Minkowski, in his book, he's an expert on space-time diagrams, and he did things with them in his book that I hadn't even imagined were possible. Now, I just stick to the simple things because I'm not totally comfortable using them, and I think there are serious ways that you can screw things up without even realizing it. But anyway, these red marks here, they represent, the first one represents an object moving through time that is at rest with the rest reference frame of the diagram. And that will describe a vertical line parallel with the time axis. Now, if we want to represent the world line of a point that's in motion, positive along the x-axis, that will describe a line at a slight slant. And if it's at a low velocity, it will be nearly parallel to the time axis. And as it increases in velocity, it will slant further and further until it becomes parallel with the diagonal, which is set to represent the speed of light. So these two straight lines on a space-time diagram will represent an object moving in an inertial reference frame. And that is that it's traveling by inertia, it's not being accelerated, and it's obeying Newton's first law. And Minkowski noted that if you have an object that's undergoing an acceleration, it will describe a curve on the space-time diagram. As it increases in velocity, the slope of the curve will continually increase until it will match the speed of light on the 45. And plotting of these curves on a space-time diagram is very tricky, and I believe it's where a lot of mistakes are made, and I'll explain more about that later. The other thing about space-time diagrams is that you can chart two different reference frames, one at rest and one in motion, on the same diagram. And the way you do that is you have a second set of axes for the reference frame that's in motion, and we designate those as x prime and t prime. And if you have an object moving, starting at the origin, moving at some velocity on the reference frame at rest, it will describe a slanted line. And then if you move into a reference frame where that object is at rest, that line will be at the same slope as the time axis. So the time axis is defined by a velocity difference between the two reference frames. And similarly, the x prime axis is at an angle similar to the t prime axis, and as you increase the velocity, those two axes swing slowly towards each other until they merge with the diagonal at the speed of light, at which point time and space have merged. And this is similar to the experience of a photon traveling at the speed of light. Photons experience neither time nor distance. The point of emission for a photon is the same as the point of absorption. The entire universe is compressed down, length contracted to zero, and those 2 points are brought together. And time comes to a stop, and the photon experiences no time in the transit. And this is represented on a space-time diagram. Now, Minkowski had a couple of other insights. One of them was that each different set of axes represents a different space-time, and it will be a set of all the simultaneous events for that level of space, which will be different from the simultaneous events at any other level of space. And if you can add up all the possible space-times from being at rest to moving at the speed of light, you can come up with the sum total of all possible simultaneous events within space-time. So if we go back to the quote, and we see Minkowski talking about an infinite number of planes in 3 dimensions, an infinite number of spaces. So what is he talking about? Is he talking about parallel universes? Well, no. He's talking about the fullness of the space that we experience on a daily basis. Let's imagine if we can take all of these space-time diagrams and begin stacking them up like sheets in a stack of sticky notes. And we start with the bottom sheet, perpendicular, time axis and x-axis with an origin. And then the next sheet, the t prime and x prime axis are very slightly skewed toward each other. And then the next sheet, a little bit more and a little bit more. And we keep building the stack until we will end up with a shape like this. And I call this a 3-dimensional phase diagram for space-time. And as I've said before on this channel, you'll see things in physics here that you won't see anywhere else. I have never seen anywhere else, and I've searched the internet for this shape illustrating a 3-dimensional space-time diagram, which encompasses all possible space-times. And I have here a 3D printed version of this, where we would have the x dimension along here and the time dimension along this corner, all the levels of space-time sweeping inward until you reach the top, where you have them merge, where this line would represent the speed of light. This plane at the base represents a system at rest, And all the layers represent all the possible inertial reference frames between being at rest and traveling at the speed of light. And one thing that this 3D print reveals is that there's a third axis that's perpendicular to both space and time and is related to velocity. And that's something important that a lot of people don't realize. Even Einstein didn't realize this. And I'll explain more about that later. So in our daily lives, we live mostly on this bottom plane. And as we move and accelerate through different phases, we move very slightly up and down in the first few layers. Now, a Formula One race car going around a track will move constantly up and down between the layers, but probably won't get very high, even at those speeds. Supersonic jets, rockets orbiting the planet move a little bit higher. At the top, we'll have photons of light, and slightly below those, we might have cosmic rays. But anything in any state of motion will have its own level within the space-time diagram. And if it is accelerated, it will move up and down between these levels. So all the world lines possible for an object moving in a single direction are captured within this concept of space-time. And it's not that there are all these different levels independent. Minkowski visualized that all of these levels are active in the daily space-time that we live in, as if they're all squeezed in to the space around us. And that sounds pretty fantastical. So if we look at the space-time diagram on edge, and in this view we have the time axis perpendicular to the screen, and we have the x-axis along the base, and we have the velocity axis running up the side. If we wanted to plot the path of an object at rest with respect to the base frame, it would appear as a point and would actually describe a line moving in and out of the screen parallel to the time axis. And if we wanted to plot the world line of an object moving at some velocity but lower than the speed of light, it would describe a horizontal line which remains within one level of the space-time because it's not accelerating. This object is moving in an inertial reference frame at a constant velocity. And that's how it would plot out in this three-dimensional phase diagram. However, if we wanted to plot the world path of an object accelerating from 0 up to some high velocity, it would form a curve, just as in the space-time diagram I showed you before. But the thing is, each point along that curve would have to be described as belonging to a different level of space-time. And in that way, in order to properly plot the curve of an accelerating body, you'd have to plot each point of its path on a different set of space-time axes. And that's not generally what's done. Usually it's just plotted on the base plane with the set of axes which are at rest. This, I believe, is an incorrect way to plot the paths of accelerating bodies. And no one usually goes through the time, though, to plot them individually on each set of axes on a different layer. So if we look at a volume of space, and you may recognize this from one of my earlier videos on space-time, we tend to think of any volume of space as being in the state of rest with respect to ourselves, and it's just our self-centered kind of point of view. This volume of space certainly has photons passing through it, certainly has radio waves, magnetic fields, probably cosmic rays, who knows what's passing through it, and they could be going through it at any possible direction. So space-time has to be ready for everything. How do we account for all these different velocities within a space frame that's at rest with respect to ourselves? Because For instance, a high-speed cosmic ray, that space-time would be length contracted along the direction of its motion. And if another one was coming through another way, it would be length contracted on that other direction. Well, how could it be length contracted on both directions at once without us noticing it? So this is what is hard to conceive for most people, is how space-time has all these different levels all at once. And it might sound like maybe Einstein's philosophy is better, either the one space or the no space philosophy. After the next couple of charts, hopefully the question in your mind will not be, how are all these levels possible? But really, how could it not be that way? So let's take the example of a two-dimensional system, and we're going to expand that into a three-dimensional system. And this is something I think we can all visualize, and this is similar to what Minkowski was talking about with the infinite number of planes when you go from 2 dimensions to 3 dimensions. I like to use points because I think it carries forward more logically. So let's describe what we know for considering going from 2 dimensions to 3. So we have a 2-dimensional plane, and there are an infinite number of points on that plane in both x and y. So if we want to go into the third dimension, we imagine a line perpendicular, which will be our third axis, or z-axis, and along that line there are an infinite number of points in the positive and negative direction. So we can write the sentence, for every point in the 2-dimensional system there are an infinite number of points in the third dimension that exist all at once. It's easy for us to see how all these points can exist all at once. If we pick some point arbitrarily off the plane, that doesn't preclude all the other points above and below from existing. And we can see this, and it makes up a 3-dimensional space. It's easy to see. It's not so hard to see in 4 dimensions. But let's think about going from 3 dimensions to 4 dimensions. So now we have a 3-dimensional system. We have our 3 axes, and we have to imagine some 4th dimension perpendicular to these 3 axes. And that's kind of hard to imagine. But we can just simply rewrite the same sentence we developed going from 2 to 3 dimensions and just change it to going from 3 to 4 dimensions. And we would say, for every point in the 3-dimensional system, there are an infinite number of points in the 4th dimension that exist all at once. So all possible 4D states can exist concurrently. So it follows logically that there isn't just a single 4th dimensional space. There is an infinite number of 4-dimensional spaces, all contained within the same system. And this is the vision that Hermann Minkowski had. So Minkowski could glimpse the full power of 4-dimensional space. And I want to add something about my 3D diagram. This 3D phase diagram only represents a single direction in space. So to imagine the fullness of Minkowski spacetime, you have to imagine any point in our world, and then this axis, which represents space, rotated to any possible orientation at that point. So Minkowski space just gets bigger and bigger and more powerful. So let's take a look into the math. Now I've represented here the very simplest forms. And Minkowski developed the full index notation for 4-dimensional vector transforms. And you can find that in this book. If we look at the expression of Minkowski space, we have the space-time interval, which is invariant under Lorentz transformation, under Minkowski space. And we have our x, y, z coordinates and a minus tc squared. All of these are squared in a Pythagorean relationship. So one thing you may notice and different from some of my other slides in earlier videos, is this minus sign. Now, this minus sign distinguishes Minkowski space, and it is something he introduced that's different. And in the earlier videos, I just wanted to illustrate the Pythagorean relationship, so I showed a plus sign just not to raise questions that I didn't want to deal with at the time. So what Minkowski did is he actually introduced, and I could more properly show this as plus ITC squared, where I is the square root of -1. And that's not really shown here, but it gives you this minus sign. And it gives you the relationship, the inverse relationship between time and space. So if we look at a transformation from a coordinate system at rest to a coordinate system at motion, and we can find that motion to the x direction, we apply the Lorentz transformations. Y is going to equal y prime. There's no change in the y direction. Z is going to equal z prime. There's no change in the z direction. X times the Lorentz transformation is going to equal x prime. And t, time in the reference frame, divided by the Lorentz transformation is going to give us t prime. So we can express the invariant space-time interval as shown here, and you can see how, as the velocity changes, there will be a corresponding change in the TC dimension as there is in the X dimension. And this is where I would like to point out the composite nature of the fourth dimension. Now, most people think and say, and if you listen to internet videos, you'll say the fourth dimension is time. Well, it's actually time and motion. It's a composite dimension. And not a lot of people deal with this. Einstein didn't deal with it, but Hermann Minkowski, I believe, understood this. That's how he could come up with the concept of all the different space-times that there would be within the universe as we know it. And that's illustrated when you consider what he described with his space-time diagram, incorporating all the different possible layers. Clearly, you get the axis perpendicular to time and space, the axis of velocity. So really, Minkowski space is more of a 4.5 dimensions, if you will, or there's another dimension of velocity that needs to be considered. So let's take a look at the timeline again. Einstein published special relativity in 1905, and in 1907, Minkowski refined it with Minkowski space. And very shortly later, at the age of 44 in 1909, Minkowski was taken away. Minkowski didn't get to see or contribute to the next 2 decades. He could conceivably have lived into the 1940s, and the next 2 decades were decades of revolution in physics. And had Minkowski lived, who knows what he could have contributed. He most certainly would have collaborated with Einstein and come up with a different, possibly better version of general relativity. So how would a multi-levels of space-time and Minkowski approach to general relativity work? Well, we see here we have a depiction of a gravity well, and there are radials, which would represent an object falling directly toward the center from any possible direction. And there are circles of constant radius, which would represent possibly the surface of a sphere of uniform density, starting with a high density sphere where the escape velocity would be the speed of light. And as we increase the radius of that sphere, it becomes less and less dense. And the surface of a sphere would correspond with any of these circles, where we would have escape velocity decreasing as the radius increases. This would work well in Minkowski space, where velocity difference defines the different level of space-time. So let's take a look a little bit more into the math of this. Now, from general relativity, Einstein came up with gravitational time dilation. Time observed on the surface of a gravitating body is equal to the actual time observed at a great distance divided by something that looks like a Lorentz transformation. And then if we go into special relativity, we have the same relationship that we saw before, where the t prime is equal to t divided by the Lorentz transformation. So let's imagine one clock greatly removed from any gravitating bodies, and we fly a spaceship past that clock at a high rate of speed. This will tell us the rate that the clock is running on the spaceship. Now let's say we also can observe a massive body some distance away, and we have a clock on the surface of that body. Well, this equation will tell us the rate of time that we expect to see from the clock on the surface of that body due to gravitational time dilation. And the TA and the T are the same clock that we are using as our reference clock, so they're equal to each other. So now let's say we want to find a velocity at which the spaceship can travel and match the time dilation that we're seeing on the surface of the planet. So we set these two terms equal, and then we see that this term under the radical must equal v squared over c squared. And we can cancel out our c squareds and then take the square root, and what we end up with is the formula for escape velocity, which means in order to describe gravitational time dilation, we only need to use escape velocity on the surface to define the rate at the clock runs, and it will be, if we have a spaceship traveling at that same velocity, the clock on board will run at the same rate as we would see on the surface of the planet. And this is a different but easier approach than what Einstein took, using gravitational potentials and doing a lot of fancy math and hard work, and finally arriving at the same conclusion that Minkowski could have arrived at very easily and very simply. So if we now apply Minkowski's approach, we would have space-time moving at escape velocity at each of these isobars, if we imagine a funnel flow. Let's go back to the figure of the gravitational well. Each of these circles could now represent the escape velocity at a given radius from the center of the attracting mass. However, velocity is a vector. It has both a magnitude and direction. And right now, all we have depicted is the magnitude, and we can compute that based on the radius. So at what direction should we point the velocity vector? Well, if we want spherical symmetry, the only choice is to point the velocity vector directly at the center of mass or directly away from it. So we end up with two solutions using Minkowski's approach. And what that has led to for me is a fluid space theory approach, where I liken these levels of space-time of Minkowski space with the velocity vector field directed inward or outward from a central mass, sort of like sink or source flow, as a flow field. And if we imagine that flow field, it's going to increase each constant radius from the mass. It's going to have the value of escape velocity, and that will be 0 at infinity, and it will go all the way down to the speed of light at the event horizon of a black hole. And if you look at the space-times, then each space-time along that path is at a different level. It's represented on the 3D space-time diagram. As you move from infinity to the event horizon, you go from being at rest to length contracted down to 0, and all levels in between. So you get this ongoing length contraction in the radial direction, which then, if we expand it back out to its full length, will cause a Euclidean cone based on the concept of Euclidean geometry to actually become a hyperbolic funnel. So this treatment results exactly the same space-time curvature as general relativity and exactly the same time dilation as general relativity. And it would explain the deflection of sunlight during an eclipse. It would explain the orbit of Mercury, the precession of the orbit of Mercury, and every other success of general relativity will be replicated by fluid space theory. And I believe that the many spaces approach of Minkowski would have led him to a similar conclusion back in between 1910 and 1920. And it would have been a much easier approach, better, more complete approach to generalizing relativity. In fact, there's another quote from the book that I have here that I find very interesting. And Minkowski says, although the physicist must now partially and newly invent these concepts, whereby they must clear for themselves, and with great effort, a jungle-like path through an unexplored territory, while quite nearby there already exists an excellent highway for the mathematicians which leads comfortably onward. He foresaw Einstein would have to take the hard way, while the mathematicians had it pretty much already worked out very easily. Now, I've said something similar. I've likened Einstein. Imagine you're at the center of a tropical island. You're trying to get to the beach. And Einstein wants to get to the beach of understanding gravitation. So he hacks his way through the jungle, climbs a volcanic ridge, rappels down the cliff face, and arrives at a beach. And he put great effort into it. Meanwhile, there's a comfortable footpath that leads through the jungle, around the volcanic ridge, to a much wider, easier, more beautiful beach. And that's exactly the same thing Minkowski foresaw and what this quote describes. So let's take one last look at the timeline. And we can realize that the death of Hermann Minkowski was a true tragedy for physics and the advancement of physics. Who knows what contribution he could have made in the next 20 years, developing quantum theory, cosmology. Distant galaxies weren't even discovered until the early 20s. That is, back in 1910 and 1905, everyone thought the Milky Way was it. There wasn't anything outside of it. And when Einstein introduced his cosmological constant, it was to prevent expansion of the universe and to create a steady-state universe consisting of only the Milky Way. Later on, when galaxies were discovered, and then Hubble discovered the expansion of the universe, Einstein had to go back and change his thinking. Possibly, if Hermann Minkowski had lived, we would have had an entirely different concept of cosmology. In fact, today, we might not even be speaking of dark matter and dark energy because he could possibly have figured that out. And we wouldn't have had Einstein's version of general relativity holding back progress. And maybe Sabine Hossenfelder could be reporting on actual progress and experience a brief moment of happiness, which would be good for all of us. So I'm not saying that I'm a new Hermann Minkowski. Far from it. He was a gifted mathematician, and I struggle with the math that he developed. However, I've come up with fluid space theory, which uses his four-dimensional vector transforms and the math of that, and I believe I have reached at least some level of his vision. Now, can I compete with Hermann Minkowski? Maybe with a little work, I can compete with his mustache, but he was in a class by himself. But when you look around for new theories and new explanations, I might be the next best thing. So until next time, I'm Hugh Manfield.